Section 1.3, Systems of Linear Equations in Two Variables. In this section, we will solve systems of linear equations in x and y graphically, algebraically using the substitution and elimination method. We can also use the calculator to analyze the systems and graph them. And finally, we will try to solve some applications using systems of equations. So I keep saying this word systems of equations. So what is a system of equations and how do you solve it and what is the solution? The definition of systems of linear equations is basically a system consists of two or more equations. In this section, we're dealing with just two equations with two variables. So something like this right here, 2x minus 2y equal to -10 slash -x plus 2y equal to 8 is considered a system of two equations. And our goal will be to find the solution. So what is the solution? The solution is the place where the two lines intersect. So this is typically going to be a point with some x coordinate and some y coordinate for consistent and independent systems. This is typically the most common scenario that we're going to be working with. This is the scenario where the lines cross at a single point. Now, there are some systems with no solutions. This happens when the two lines that you're working with are both parallel lines. Remember, these systems are systems of linear equations because the x is raised to the power of 1, the y is raised to the power of 1. This represents the equation of a line, as we saw in the previous section. And in this case, both equations are written in what's known as the standard form. So if your problem does not have a solution, it means that the lines must have been parallel. And to describe this whole scenario with just one word, instead of saying a lot of words, we say that the system is inconsistent. So the word inconsistent tells the person you're listening to you that the lines are parallel, therefore there are no solutions. Now, it happens every once in a while where the two lines I'm working with are actually on top of one another. This is the scenario that we would describe as consistent because obviously the lines will have intersections. As a matter of fact, every point on the first line will also be a point on the second line. That's where the word consistent comes from. And we will use the word dependent to describe the scenario where the lines are overlapping one another. And again, consistent means that there's a solution. Dependent means that there is one solution in this case because the lines are overlapping. So the keywords are consistent and dependent. So the word consistent means there's an intersection point or the lines are crossing or touching at some point. And if you use the word independent after that, it means that there's one value where the two lines intersect, and the value is going to be an ordered pair, like two numbers, like 0, 4, for example, or 1, 2. Or in this other case, it could be many, many points. The lines could be on top of each other, which means that the system is going to be dependent. The middle scenario, when the lines have no solution because they don't intersect, we just use one word to describe that. We don't say consistent anymore. We just say inconsistent, and we don't use the word dependent or independent because there is no solution. So we don't need to describe it anymore. We just say inconsistent, meaning no answer. So the first thing we're going to do is, how do you check if your solution is correct? So that's what we're going to do in example number 1. We're going to determine if the ordered pair, the given ordered pair, so there's somebody suggesting that this might be the answer to this problem. How can we confirm if this is true or not? How can we check that 0, 4 is the solution of that problem? This is a useful step to do at the end of your process if you have extra time on a test or if you just want to be super aware and super confident then that your answer is correct, you can do the following. So you're going to take the first equation, which is 2x minus 2y equal to -10, and you're going to plug the x value and plug the y value into the equation and see if you get the same number on both sides. So in this case, it will be 2 times 0 minus 2 times 4 equals to -10. Now, I don't know if this is going to be true or not, so I'm going to put a little question mark on top of the equal to remind me that this is not necessarily true. I'm still checking. If the left side and the right side turn out to be the correct answer, they both are equal to each other, then we are confident that 0, 4 belongs on the first line, and we can continue and check if 0, 4 belongs also on the second line. If it fails, then we can stop and we can say since 0, 4 is not even on the first line, then it's probably not a solution of the problem because it needs to be on both lines to be considered a solution. So let's keep checking. 2 times 0 is going to be 0. 2 times 4 is going to be 8. So 0 minus 8, is that really the same thing as negative 10? And unfortunately, negative 8 is not equal to negative 10. No, this is actually false. So what can we say now? We can claim with confidence that 0, 4 is not a solution of the system that was provided to us. Okay, so to be a solution, you have to check both equations. If both are true, if you get the same number on both sides in both equations, then the ordered pair that you're provided with is a solution. If not, if it fails for one of the equations, you can stop. You don't even have to check the second equation. You can stop there and say that the ordered pair that you're provided with is not a solution. So let's give it one more shot. We have the same system on the second problem, but we have a different order pair, negative 2 and 3. So the first equation is the first equation is negative x plus 2y equals to 8. And somebody's telling me to try negative 2 for the x and 3 for the y. So I have to be super careful here because there's a lot of minus signs. So I have a negative, and the x itself is negative 2. And then I have 2 times the 3. Is that the same as 8? So plug the x negative 2 in, plug the y 3 in, and let's confirm. Negative negative is going to be positive 2, and 2 times 3 is going to be 6. Is 2 plus 6 the same number as 8? Yes, this is true. That's looking good so far because the ordered pair at least belongs to the first equation. So it lives on the first equation. Now we just have to confirm that it also satisfies the second equation. When we say the word satisfies here, we mean that negative 2 and 3 also makes both sides equal. So let's give that a try. So the second equation is 2x minus 2y equals to negative 10. And I need to plug in x negative 2, y 3, and see if I get the same thing on both sides. So again, x is negative 2 and y is going to be 3. And those numbers are usually numbers that you have to find yourself. In this first page, or the first part of the section, somebody's suggesting us to try them. And let's see, negative 3 times 2 is going to be negative 4. 2 times 3 with the negative sign is going to be negative 6. Is it true that negative 4 minus 6 is the same thing as 10? And the answer is yes again. This is, in fact, true. So, in conclusion, what can we say? We can say that the order pair negative 2, 3 is a solution of the problem. Notice that we said it is a solution. We didn't say it is the only solution because it could be possible that these lines are coincident, which means that it could be possible that these lines are on top of each other, which means that there may be more than one solution. This is the reason why I'm writing negative 2 comma 3 is one possible solution. Okay, so how do you find these ordered pairs? There are at least 3 different ways that we're going to describe in this section. We can either use the graphing method, we're going to use the elimination and substitution method, and let's begin with the graphing method. So we know that these equations in the system are basically lines. So we should just graph them and see where they intersect on the xy plane. If they intersect at a specific point that's on the grid, that's easy to read, then we're done. But if the graph is kind of off somewhere out of the picture or whatever, then we may need other methods. So in this problem, we're asked to solve each system by graphing, and we have to describe the situation that we're dealing with. Is the system consistent? Is it inconsistent? And when it is consistent, are the equations dependent or independent? So let's begin with equation 1, which is the equation x plus y equal to 4. So in this case, I think the easiest option to graph is to use the tabular method and plug some values for x and see what we get for y. To do that, I'll just start by rewriting the equation as y equal to negative x plus 4, so that when I make my table, it will be a lot faster to get the values for y. And the numbers I'm going to pick for x are going to be 0, 1, and 2. or you can pick 0 to 4, you can pick 0, -3, -6, whatever you want, whatever numbers that seem to please you, that's fine. I'll go with 0, 2, and 4. So if x is 0, I plug it into the equation, and my y will be equal to 4. If x is equal to 2, I plug it into the equation. I'll end up with -2 plus 4, which means that the y is going to be just simply 2. And finally, if I plug 4 into this equation, the y that I get is going to be 0. So this gives me a bunch of coordinates and a bunch of points. So the first point I'm getting is 0, 4. The second point I'm getting is 2, 2. And finally, the last one is 4 and 0. So plotting those points and graphing this line, we get the following. Okay, so this is a graph of equation number 1, and it's done. So now we must do something similar to this for equation number 2. So let me pause the video and write down the details for that, and I'll unpause. In the meantime, see if you can get the same graph as the one I'm about to get. Okay, in my table, the ordered pairs are 0 and -2 for the first point. The second point is 2 and 0, and the final point was 4 and 2. So all I need to do now is plot the points 0, -2. When x is 0, the y is -2. That's the same as the y-intercept of the line. When x is 2, the y turned out to be 0. And finally, when x was 4, the y was 2. So those are my points, and now let's connect the dots and graph the line. Okay, so the last step that we need to do now is determine if there's an intersection if there's an intersection point between the two lines, and try to decipher the values where the lines are intersecting. And it's clear to me that the lines are intersecting somewhere here. So all we have to do is be able to read off the x-coordinate and the y-coordinate. It seems like the x should be somewhere in the middle between 2 and 4, so it's going to be probably a 3. And the y-coordinate will be somewhere between 0 and 1, so the answer should be 3, 1. So this is the solution of the system. It's 3, 1. And as we can tell, this is the only answer. There are no other intersection points between equation 1 and equation 2. So we will use the words consistent and independent to describe this whole scenario. Okay, so that's the end of part 1 of example number 2. And I'm going to pause the recording here for a few seconds and give you a chance to work on part 2 on your own, and I'll give you the answer in a few seconds. So pause the video here, please, and try it on your own. Okay, so here's the graph that I received. I tried to use a different method for this problem just to show you another variation on the table method. So instead of writing the table like we did in the previous problem, you could just write down all the numbers one by one without using a table. And in this case, I took the liberty of letting x be 0, then y be 0 for each equation without modifying the equation itself. So in the first equation, if I let x be 0, then the y turns out to be 2. And if I let y be 0, then the x will be -6. Similarly, in the second equation, I let x be 0, then the y be 0, and I found the numbers -1 and 3. This gives me a couple of points on the graph, and it goes against what I told you before, which is you should make 3 points, but I'm confident that at this point in time, you're able to graph lines. And as we can see from the graph, it doesn't appear that there's any intersection points. So the answer to this problem is that there is no solution. Okay, so how do we describe to somebody who's not watching all this what we're dealing with? So to do that, we can just say the word inconsistent. So the word inconsistent just means that you're dealing with special graph, the graph of the lines, and the lines are parallel. So there is no intersection point. Okay, again, just like before, pause the video here for a few minutes and try to solve this problem, and I'll show you the answer in a few seconds. Pause here and try this on your own. Okay, in my case, again, I decided to use a tabular method, and this time, because the x is on one side in the first equation and the y is on the other side, I decided to pick two values for y and determine the x coordinates. So that gives me -1 for the x and 0 for the y, 2 for the x and 1 for the y. And when I plot them, I get the graph of the line. And for the second equation, I did something similar. I just decided to let y be 0 and y be 1, and in return I got the same number that I got for equation 1. So the lines are overlapping in this particular instant, which means that every point on the first line is also a point on the second line. So how do we say this? This is the scenario where the system is consistent and dependent. So the solution can be written in many different ways, but here's one option. We could put a curly brace and then x comma y inside parentheses. So we're saying to the reader, take anything you want as an ordered pair, as long as, that's what this little vertical sign means, and you could just write down one of the equations that are in the question. So in this case, I could write x equal to 3y minus 1 and then close the curly brace. So this is the way we present the answer when we're dealing with lines that are overlapping. This is just, like I said, one of the many options. And what does this actually mean? This means that you can take any ordered pair that is on the first line and it will be automatically a point on the second line. And finally, to describe the scenario, we use the words consistent, dependent. Okay, so as you can tell, this first method of graphing the lines is not always great. You have to do sometimes a lot of work. You have to graph the lines and you have to hope and pray that you can read off the intersection on the grid. So it's not the most reliable option. This is why we have other methods like the substitution method and the elimination method, which we're going to do next. So in substitution method, there are some steps that we can follow along to solve the problem, but the bottom line is you're going to take one equation and you're going to solve for either the x or the y. In my case, in the second equation, I already have x equal to y plus 4. We're going to take those numbers, those quantities, y plus 4, and put it into the other equation wherever x is, and then solve the linear equation that we get. This should give you one of two values, either x or y, depending on your choice. And once you have one of the numbers, it's easy to get the second one. You just need to do some back substitution. So in this particular instant, my first equation is 2x plus 3y equals to 13. And then I have the second equation, which is x equal to y plus 4. So I'm going to grab the y plus 4, and I'm going to plug it into equation number 1, wherever the x used to be. So I'm going to write equation 1 becomes, what does it become when I replace x with the quantity y plus 4? Becomes 2 times y plus 4 plus 3y equal to 13. This equation has only one single letter, which is the letter y, or one single variable. So it's easy to solve it. We know how to do that because we learned in a previous section. So we multiply the 2 to get 2y plus 8 plus 3y equals to 13. We have some like terms. The 2 and the 3y are like terms. The 2y plus 3y is going to be 5y. And I'm going to remove the 8 and put it on the other side with the 13. To remove it, I need to subtract 8 from both sides. So if I subtract 8 from both sides, what do I get? I get 13 minus 8, which is 5. And now this tells me that the y value is 5 divided by 5, which is exactly equal to 1. So since I have what y is, I have the value for y, all I need to do now is plug that number back into the original problem in one of the equations and get the x value. It's easier to plug it into the second equation because the second equation already has x equal to y plus 4. So I'm going to write, but wait a second, I remember that x equal to y plus 4, and I just determined that y is equal to 1. So let's plug that value in and end up finding x. So x is going to be 1 plus 4, and 1 plus 4 is clearly equal to 5. So what's the solution of the problem? The solution of this problem is going to be 5, comma 1. 1 for the y and 5 for the x, which means that the problem is consistent independent. As a reminder, consistent means you were able to find an answer. Independent means that you were able to find one single value. The lines are not coincident. The lines are not overlapping. They just touch in one single spot. And that spot is 5, comma 1. And that's the end of example number 3. Okay, so that's a quick glimpse into the substitution method. What about the elimination method? Again, there are some steps that you can follow that are on the screen. Take a minute to pause the video if you want to read them or look at the handout. But the bottom line is you want to eliminate the same variable from both equations. So in my particular problem, example 4 says use the elimination method to solve the system. I have x minus y equal to 9, then I have x plus 3y equal to 7. I can decide if I want to eliminate the x or the y and work accordingly. So let me begin by writing down x minus y equal to 9, and then x plus 3y equal to 7. I'm going to decide to eliminate the x. So what does that mean? Well, if I multiply the first equation by -1 straight across, then I would end up with negative x, and then -1 times negative y is going to be positive y. Finally, 9 times -1 is going to be -9. And if I keep the same second equation, I don't change it, I will end up with x plus 3y equal to 7 again. Notice how the x now on the first equation and the second equation, if added with each other, it will disappear. And that's exactly what I'm going to do, and that's exactly why we call this the elimination method. You're trying to eliminate the same variable, and you do that by multiplying one of the equations by a specific number. So in this case, I decided to eliminate the x by multiplying it by -1 on the first equation. Now, another person could have decided to multiply, for example, the first equation by 3. That way, you end up with a 3y with a negative in front of it, and a 3y on the second equation. That will eliminate the y's. You get the same result, but the other person will get the y first or the x first, and I'll get them backwards. So it doesn't matter really. You can do either option. So back to my problem. If I add the equations down, negative x plus x will be 0, and I'm not going to bother writing that. Next, I've got to add the y with the 3y. That's going to give me 4y. And finally, -9 added to 7. That's going to be -2. And so the y will be -2 divided by 4. Another way of saying that is to say -1/2 because we can reduce it. Now that we know the y value, we'll just grab it and plug it again into one of the original equations in the original problem. Doesn't matter which one you do, just pick the one that seems easier to you. I'm going to go with equation number 1. So I'm going to write, but wait a second, I remember that x minus y is 9. So if I replace y with -1/2, what do I get? I get x minus -1/2 equals to 9. Okay, so the y value is going to be replacing the y variable. And now I have x plus 1/2 equals to 9. And I just need to subtract 1/2 from both sides of the equation. So 9 minus half is going to be 8.5 basically. So 9 minus 1/2. And we don't really like decimals in math, so I'm going to try to write the answer as a fraction. In case you don't remember how to do this, you'll have to kind of pretend there's a 1 under the 9 and then find the common denominator, so multiply by 2 on top and bottom. So this now will be 18 minus 1 over 2, or that's the same thing as 17 over 2. So that's another way of saying 8.5. So 17 over 2 is the solution that I'm getting for x. Okay, so now how do I present my final answer? We present it as an ordered pair where x is first and y is second. So x is 17 over 2 in this case, and y was negative 1/2. And the scenario is described by using the words consistent, independent. So consistent means we found an answer. The answer consists of two numbers, and independent just means that the two lines in this problem are overlapping just in one spot, and that spot is x 17 over 2, y negative 1/2. Okay, so in example 4, we saw the elimination method, and example 5 basically tells us to use any method that we prefer to solve the system. So we can use either elimination or substitution to solve the given system. It's up to you. You can decide whichever method you prefer and just stick with it forever. Just know that sometimes somebody will want one method, so it's a good idea to know both options. And for certain problems, sometimes elimination is better, sometimes substitution is better. So you want to be flexible, you want to know both options. And my first problem, or my first part, is 6x minus 3y equal to negative 3, followed by the second equation, 4x plus 5y equals to negative 9. Again, the question is to use elimination or substitution to solve the system of equations. Then we have to decide if the system is consistent, inconsistent. Then we have to say if it's dependent or independent. So let's start by writing down the equation 6x minus 3y equals to negative 3, and 4x plus 5y equals to negative 9. And we must decide which method we want to use. Do we want to use elimination or substitution? I think in this case, I'll go with the elimination method, and maybe I'll try to eliminate the y's. Why am I going to work with the y's? I can already see that one of them has a negative 3, the other one has a positive 5, so that's kind of nice that one of them is positive and one of them is negative. And what I'll do is I'll multiply the first equation by 3, and I'll multiply, sorry, the first equation by 5, and I'll multiply the second equation by 3. So this will put 15 in front of both y's, and then I'll deal with the damage that happens on everything else. So let's give this a shot. 5 times 6x will be 30x. 5 times negative 3y is going to be negative 15y. And 5 times negative 3 is going to be negative 15. So that's my first equation rewritten. The second equation, when I multiply by 3, I get 12x plus 15y equals to negative 27. So as you can see, the y's now have 15 and negative 15 in front of them. So if I add those two up, then my answer will not have any letter y's, and it will be easy to solve for x afterwards. Now, elimination is really good when your equations are already in standard form. So if one of the equations had the x's and y's on the other side, then elimination will probably not going to be a good choice. Maybe in that case you want to use substitution, or maybe just rewrite the problem so that you can use elimination. In this case, everything was nice and convenient, so that's why I'm doing this. So let me go ahead and add 30 and 12x. That will be 42x. The 15 and the 15y will go away. And finally, negative 15, negative 20. That's negative 42. And so x will be negative 42 divided by 42, which will be negative 1. So I'm dividing basically the negative 42 from this side of the equation by the 42 from the other side of the equation, and that's how I'm getting a negative 1 for the x value. So x is negative 1. That's awesome. We have one of the two values that we need. All we have to do next is find the second value, which is the y. And so to do that, we'll just need to grab any equation from the problem. Typically speaking, you want to use one of the original problem equations, just because they don't have any errors, you haven't modified anything. And I think in this case, I'll go ahead and use the second one. It doesn't have too many negative signs, and that's kind of nice because negative signs usually screw things up for us. Okay, less chance to make an error if there's fewer minus signs. So I know that 4x plus 5y is negative 9, so let's remove the x and replace it with negative 1. So 4 times negative 1 plus 5y has to be equal to negative 9, and x was negative 1. That's why we plugged in that value. So this will be negative 4 plus 5y equals to negative 9. We're going to move the negative 4 to the other side by doing the opposite. So we're going to add 4 to both sides of the equation. And when we do that, we end up with 5y equals to negative 5, which means that y is going to be negative 1. So I'll erase this just to save some space. And there we have it. Y is equal to negative 1. So we got one answer for the x, one answer for the y. So what's our solution? Our solution is going to be the ordered pair negative 1 for the x, negative 1 as well for the y. So remember, this is an ordered pair. The order matters. X always goes first, y always goes second. It has to be in alphabetical order. And to describe this whole thing, we will use the words consistent, independent. Okay, so that's the end of part 1 of example 5. Okay, in part 2 we have the equations x minus 3y equals to negative 1, followed by negative 3x plus 9y equals to 5. So let's see, what should we do? To me, it seems like it's a good idea to again eliminate one of the variables. That usually seems to be the best option when we have equations in standard form. So what I'm going to do this time is I'm going to multiply by 3, but just on the first equation. This will put 3x on the first line, and we have a negative 3x on the second line. So hopefully that will eliminate the x's, and it will be easy to find the y. So we'll put the 3, and we'll multiply everything on the first line by the 3. Notice that whenever I make any modifications to the problem, I always like to write both equations down, and I like to put the curly brace so that way I have the most up-to-date version of the problem in the same spot. I don't have to keep looking back or back to see what I did. This is the brand new problem with all the modifications on it. And so now I'm just going to go ahead and add the equations together. And if I add them together, the 3x and the 3x will cancel out, so that's going to be 0. I'm not going to bother writing it down. Negative 9y and 9y will also cancel out. Well, I need to write something on the left, so I'm just going to put 0 this time. And finally, negative 3 and 5, when added with each other, we will get 2. However, there is no variable. All the variables got eliminated. We tried to eliminate only the x, but both x and y disappeared. And now we have an equation that says 0 is equal to 2, which is pretty much nonsense. This is a false statement. 0 is not the same as 2. So what are we dealing with? We are dealing with one of those problems where we have no solution. Basically, the lines in this problem are parallel, and because they're parallel, there is no intersection. The word we use to describe this whole thing is the word inconsistent. So you can say no solution, and you can write inconsistent to make the reader understand that your lines are parallel, therefore there is no ordered pair. Okay, moving on to the third one. We have x plus 3y equals to 2, and 3x plus 9y equals to 6. So you can again try elimination or substitution. Since I've done elimination a few times already, I'm going to do substitution this time. So I'm going to take the first equation and I'm just going to isolate the variable x. The x already has a 1 in front of it, so that's kind of nice. If I isolate the x, I'm going to end up with x equals to negative 3y plus 2. So now that I have the quantity that is equivalent to x, I'm going to take it and put it into the other equation that I haven't used yet. So equation number 2 becomes 3 times the x plus 9 times the y equals to 6, but x is negative 3y plus 2 because that's the quantity we found from equation 1. And let's FOIL everything out. multiply everything out, distribute, and combine like terms. 3 times negative 3y is going to be negative 9y. 3 times 2 is going to be 6. And then 9y equal to 6. The 9y minus 9y will add up to 0. So we now have 6 equals to 6. And this is definitely a true statement. So there are no variables. We only have 6 equal to 6. And so what does this mean? In the previous problem, we had 0 equal to 2, which meant we had a false statement, which means the lines were parallel. If your numbers are equal on both sides, so in this case 6 equals 6, that means that your lines in this problem are coincident, and that means that the lines are overlapping. The lines are on top of each other. So how do you write down the solution in this case? As a reminder, the solution, we use curly brace, and we put x comma y inside parentheses. We put the little vertical sign, the little vertical slash, which means you can pick any x comma y as long as they satisfy, and then you write one of the equations that you see in the problem. It doesn't matter which one you pick. I'll pick the original first one, x plus 3y equals to 2. So I'm telling the reader that you can pick any ordered pair as long as it satisfies this equation. As long as the pair satisfies the equation x plus 3y equal to 2, then that ordered pair will be a solution for the problem. And the words we use to describe this are consistent dependent. Okay, so that's the end of that part. Okay, so the last paragraph that we have in this section reminds us what the words consistent and inconsistent means, what the words dependent and independent means. So take a moment to pause the video and read that in case you still don't understand the difference between the two. And in the last part of the problem, or the last part of the section, we will work on some applications. And this is one of the business applications that deals with break-even point. So in business calculus, we will have a few different applications mixed in, and this is the first one. We're talking about cost and revenue. The cost is the cost of making some item. Revenue is the money that your business is going to have coming in. And in this case, for example number 6, it says given the cost function, which is c of x. So the c is the letter we use to refer to cost. X just tells me that this is the letter that we consider the independent variable. It's the letter that represents the number of items that you're selling. So the cost of making x items is 0.8x plus 35,000. The revenue function, usually it's called R of X, so that we can remember the word revenue. This is basically the income that's come into your business. It again depends on the number of items you're making or selling in this case. And in this case, the revenue is represented with 1.55x. And the question is asking us for the break-even point of the profit function afterwards. So the break-even point first, and then the profit function after. So let's start with the break-even point. The break-even point is the point where the revenue and the cost are the same. So to find the break-even point, I'll need to set up the equations r of x and c of x to be equal to each other. And the cost equation is 0.85x plus 35,000. And the revenue equation is 1.55x. So revenue and cost. We just have to solve this equation for x to determine the break-even point, which means we have to figure out how many items we need to sell so that our costs will be the same as our income. That's the point in time where you typically don't want to be as a business. You want to be selling more items so that you can have some profit. But we'll talk about that in a few seconds. Now, on one side of the equation, I have 1.55x. On the other side, I have 0.85x. So it seems like a better idea would be to move the 0.85 to the 1.55 since 0.85 is smaller. And I'll just subtract 0.85x from both sides to do that. So we'll have 35,000 equals to 0.7x when we subtract 1.55 minus 0.85. And again, between the 0.7 and the x, there's nothing, but that implies that there's multiplication. So to remove that 0.7, we will have to divide both sides of the equation by 0.7. So 35,000 divided by 0.7 is going to be 50,000. So x will be 50,000. So we need to sell 50,000 items to break even so that our cost will be the same as our revenue. Now, what is the profit equation? The profit is typically referred to with capital P of X. The profit equation is the revenue equation minus the cost equation. So to get the profit equation, which is what they're asking for, they want the profit function, we will have to take the revenue, which is 1.55x, and subtract the cost equation, which is 0.85x plus 35,000. Now be careful. The cost equation has multiple items or multiple factors, so make sure you surround them with parentheses so that the minus on the front goes to every factor inside the parentheses. So my profit equation or my profit function will be 1.55x minus 0.85x minus 35,000 because the negative has to distribute. And finally, the profit equation or function will be 0.7, or you can write 70 if you like, x minus 35,000. So ideally, as a business person, you want to be selling more than 50,000 items so that you can be making some profit. If you sell less than 50,000 items, then your costs are still higher than your revenue and you're going to be in the negative. You're going to be in the red and you're going to be losing money in your business. So try to sell more than 50,000 items. Okay, let's look at example 7. Example 7 says a company that manufactures boxes recently purchased $2,000 worth of new equipment to make gift boxes to sell to its customers. The cost of producing a package of gift boxes is $1.50 and it is sold for $4. We want to find the number of packages that must be sold for the company to break even. So the difference between this problem and the previous one is that the equations for cost and revenue are not given to us, so we have to provide those ourselves, then find the break even. Let's start with the cost function. So the cost is C of x. This is the cost function. And in this particular problem, we're told that the company had to purchase $2,000 worth of new equipment just to make the gift boxes. This is what we normally call the fixed costs. So in this case, we will start by writing the 2,000 down next to the cost. So this is just the cost of buying the equipment or renting the warehouse or whatever. And then on top of that, when you make a package, you have to spend $1.50. Now that's $1.50 per package, so I'm going to write 1.50 and then I'm going to multiply by x. So what is x in this case? X is the number of items. So it's the number of items that we're making or the number of gift boxes that we're making in this particular problem. So that is what X represents in this case. Now, what about the revenue in this problem? How much money will I get in return for making all these boxes? The revenue is the income. Now, when I sell a box, I'm selling it for $4, and hopefully I'm selling X boxes, so that's going to be 4X. So this is my cost and revenue equations already determined, and now I need to find the break even. So to find a break even, I need to make the cost be the same as the revenue. And so that means I need 2,000 plus 1.5x to be equal to 4x. Solving for x, we need to remove the 1.5x and put it on the other side. So we'll subtract 1.5. So this means 2,000 will be 4 minus 1.5. That's going to be 2.5x. And again, the 2.5 is being multiplied by the x. So in order to remove the multiplication, we'll have to divide by 2.5 on both sides of the problem. So what is x going to be? I'm getting 800 as my x. So I need to sell 800 gift boxes to break even so that I'm not losing money, but at the same time, I'm not profiting anything yet. This is just the number of items or the number of gift boxes that must be sold so that we have zero profit. So we're not in the green, we're not in the red, we're just coming out even. And I will leave example 8 as practice for you. The difference between example 8 and the previous two examples is that we're talking about the equilibrium price rather than the break-even point. It is the same idea. The difference is we're talking about the price versus the number of items. And so take a moment to read the problem, set it up, pause the video, and I'll flash the solution here in a few seconds. Pause the video now, try to solve the problem, and I'll give you the answer in a few seconds.